Kinetics of particle, Newton's second law, force, mass, and acceleration. Until now, we have analyzed motion of objects without considering the force that caused them. In this chapter, we relate cause and effect by drawing the free body diagram of an object to identify the force acting on it. We can use Newton's second law to determine the acceleration of the object. Alternatively, when we know an object's acceleration, we can use Newton's second law to obtain information about the force acting on it. Let's look at one of the applications of kinetic particle in real world. When we are going to design a good ramp, we must analyze all of the forces acting on the wheelchair. Newton's second law of motion. If the resultant force acting on a particle is not zero, the particle will have an acceleration proportional to the magnitude of resultant and in the direction of the resultant. Newton's second law of motion is sum of the force equal ma. This form of the equation is for a constant mass system. In a static course, we talk about Newton's first law. In Newton's first law, an object will remain its original state of motion, rest or moving at a constant velocity in a straight line. If there is no unbalanced force acting on it, the sum of the force equals zero and the acceleration is zero. In dynamics, we use two unit systems, SI unit and US customary unit. In SI units, force is usually expressed in newtons, mass in kilogram, and acceleration in meter per second squared. In US customary units, force is usually expressed in pound, mass in slug, and acceleration in feet per second squared. We can write the Newton's second law for rectangular component like as below. Sum of the force in x direction equal max and the sum of the force in y direction equal may, and the sum of the force in z direction equal maz. Before to solve any problem related to this part, we have to know that how to draw a free body diagram and kinetic diagram. The free body diagram is the same as you have done in static. We will add the kinetic diagram in our dynamic analysis. First, isolate the body of interest. Second, draw your axis system. Maybe you can use the Cartesian coordinate system, polar system, and path system. Add in apply forces. For example, 225-pound pulling force, mg as a weight, and etc. Replace support with force, for example, like as normal force. Finally, draw appropriate dimension, usually angle for particles. Look at this example. This is the free body diagram, and the right side is showing the kinetic diagram. In kinetic diagram, we have max and may. For free body diagram, the 225 Newton applied to the box, so box move along the direction of this force. So we assume x-axis is a positive toward the motion. The friction force, Ff, always opposite the direction of motion. N as a normal force, perpendicular to the surface. And finally, weight as mg is in the negative y direction as always. Example. Draw the free body diagram and kinetic diagram for the collar B. Assume there is friction acting between the rod and collar. Motion is in the vertical plane and theta is increasing. This is the free body diagram and kinetic diagram of collar B. We draw the kinetic diagram in polar system or radial and transverse coordinate. We have MAR and MA theta. For free body diagram, FF as a friction force between the rod and collar B, opposite the direction motion of collar B. Mg is the weight of collar B. Again, the weight force is in the negative y direction as always. And N is a normal force always perpendicular to the surface. Another example. The 100-pound crate is released from rest on the inclined surface at time 0. The coefficient of friction between the crate and the inclined surface are μs is 0.2 and μk 0.15. How fast is the crate move at time 1 second? First of all, we have to draw a free body diagram of the crate. We have the friction force, normal force, and the weight. First, we assume that the crate is stationary. Use the equilibrium equation to determine the friction force necessary for equilibrium and the normal force. So the sum of the force in x direction and y direction equals 0. Equation of equilibrium. We find the friction force and the normal force. The maximum static friction force, μSN, is 18.8 pounds. This value is less than the friction force necessary for equilibrium, so the crate does slip. Now we can use the Newton's second law to determine the crate acceleration. The magnitude of the friction force on the slipping crate is μk n. From this equation, we can find the acceleration. In previous chapter, we learned how we find the velocity from the acceleration. When we integrated from acceleration, we find the velocity equation. Now this is the equation of the velocity. At time 1 second, velocity is 6.47 feet per second. Next example. A 200-pound block rests on a horizontal plane. Find the magnitude of the force required to give the block an acceleration of 10 feet per second squared to the right. The coefficient of kinetic friction between the block and plane is 0.25. First, resolve the equation of motion for the block into two rectangular component equation. Second, unknown consists of the applied force and normal force from the plane. The two equations may be solved for these unknowns. Okay, first we draw the free body diagram and draw the kinetic diagram. In kinetic diagram, we have the acceleration only in the x-axis. So the acceleration in y direction is 0. We have also the normal force, friction force, weight, and this is the P. We write the second Newton law for in the x direction. The sum of the force in x direction equal mR. We resolve the P in the X direction, P cosine 30 degree minus 0.25 Newton equal M, this is A, acceleration, M times A. For the Y direction, the acceleration is 0. So we have sum of the force in Y direction equals 0. N minus P sine 30 degree minus 200 pound equals 0. From these two equations, we can easily find these two unknowns, N and P. P is 151 pound. The mass of each box is 14 kilograms. 1 second after they are released from rest, they have moved 0.3 meter from their initial position. What is the coefficient of kinetic friction between the boxes and surface? Okay. From the example, we know that 1 second after they are released from rest, they have moved 0.3 meter from their initial position. So we can use the kinematic information from previous chapter to determine the acceleration. We have a constant acceleration. This is the equation of position for constant acceleration. When we substitute the given information, we find the acceleration is 0.6 meter per second square. After that, we have to draw a free body diagram of boxes. Okay, this is a free body diagram for box A. This is a free body diagram for box B. As you can see, we have only the acceleration in the X direction for both boxes, is meaning the acceleration for Y and acceleration in Y direction is 0. So from the free body diagram, we have 4 equations of motion. When we solving this equation, we find T, NA, NB, and mu k. This is the answer. Mu k is 0.202. Last example. The 2 kilogram object is constrained to move in the XY plane. The total force on the object is given as a function of time by sum of the force equals 6I plus 2tj. At time 0, the object's position is 5I plus 3j meter, and velocity is 12I plus 5j. What's the object position at time t3 second? Okay. Use the Newton's second law to determine the component of the acceleration. We find the acceleration in X direction and Y direction. Now, from the previous chapter, we know that by integrating from the acceleration, we can find the velocity. At time 0, the acceleration in the x-axis is 12 meters per second. When we integrate it from both sides, we find the velocity in x direction. For y direction, at time 0, the velocity is 5 meters per second. When we integrate it from both sides, we find the velocity in y direction. And finally, for find the position of particle, we integrated from velocity in x direction and y direction. At time 0, the position of particle in x direction is 5 meters. We find the position of particle in x direction. For y direction, at time 0, the position of particle is 3 meters. Now this is the equation of position in y direction. At time 3 seconds, we find the position in x and y direction.